Correspondingly, we have the delta max. This is the maximum amount of swing possible inside the rotor. So the rotor angle swing can be up to this. So the A is our initial operating point. So from A to G, that is the maximum limit of swing. Beyond that, our system will fall in the unstable state. That is the case. And when we apply the equal area criterion here, so these two areas are actually same. So these two area A1 is equal to area A2. Then after that we calculated the expression of delta max, right? This was the expression of delta max. This equation number 10. And this is a non-linear equation, that means we can solve it analytically. So we have to take help of iterative techniques to solve this equation for delta max. And for that we took the help of Newton-Raphson method, right? And for that first we have to convert our equation into this general form, that is the f of delta max will be equal to c. Here in the left side you can see that this is the function of delta max, also this is the function of delta max, right? So the left side, the whole portion of the left side can be treated as f of delta max, and the right side is actually the constant c. Why constant? Because this delta naught is the rotor angle at the initial operating point, this angle, right? So we should know this one beforehand, right? Or actually we can calculate it very easily. So this is a known quantity. That's why this cos delta naught will be a constant value. That's why this can be termed as c. Now we have to apply the Newton-Raphson method. The first step is to make an initial guess, initial estimate. And here we have to do it intelligently, because we know that our delta max will lie in between this pi by 2 to pi, in between 90 degree to 180 degree, right? That's why we will take the initial case as like this. Let's say our delta max initial is it's 120 degree. Then the step 2, we have to apply the Newton-Raphson algorithm to obtain this value. Delta max evaluated at the iteration number k, and it will be equal to c minus f of delta max evaluated at k. K means we know this value because this is our initial case, right? So f of delta max means this left side. So in this side we will put the initial value of delta max, let's say that is 120 degree. Then we will get some numerical value, right, from this portion. And c is also known to us. This is actually cos delta naught divided by the df over d delta max, and evaluated at delta max of k. So in the last class we actually saw that the differentiation of this term, we have to apply the UV formula for the first term, and the second term is we must straightforward. It will be simply minus sine delta max. Okay, and then finally we will get this thing. If you do the derivative of this term, then you will get this thing. Okay, and here as well you have to put the value of delta max k. Let's say this is 120 degree. You will put this value here, then you will get some numerical value here as well in the denominator side. So this thing will give you one numerical value for this delta max, and that value will be needed to calculate the delta max for the next iteration, the updated delta max. It will be the previous delta max plus delta max of this iteration, right? Okay. Then in step 3 we have to continuously check the convergence criteria, the stopping criteria. So we have to take the difference between these two consecutive delta max values, and if this value falls under this tolerance value, let's say this is the epsilon, then we will stop the iteration, and the final value of that iteration will give us the final value of delta max. Okay? That will be the case. delta max is calculated, we can find the value of delta 1. Okay. Because delta 1 means the point P. Okay. So this is the point of intersection, because in this side this is the accelerating area and this is the decelerating area, right? And this is important to know the PM1 value, because PM1 is actually the P value at this point. So what is P, and in this point it is P max sine delta 1, right? Also we can take PM1 as P value of this point, that is the P max sine delta max. Okay. So we can take any of the expression. So here we have taken the PM1 as P max sine delta 1. Also this can be equal to the P max sine delta max. Okay. So if this P max should be cancelled out, then the delta 1 can be expressed as pi minus delta max, because this can be written as sine pi minus delta max, because sine pi minus delta max will give you back this sine delta max. Okay. So this is in the second quadrant where actually sine is positive. Also this is the even multiple of 90 degree, that means it will return the sine, so it will be same. So sine will be cancelled out, so delta 1 will be pi minus delta max. Okay. That means the summation of this delta 1 and delta max will always be quantitative, okay, at any point or at any value of this Pn1. If you take this Pn1, then here as well this delta 1 and this delta max, the summation of these two will give you the quantitative. Now with this information we want to solve the example 11.4 that is given in your Khadi Sadat book. So this is our single machine infinite bus system. Okay. This is the synchronous generator. This is the transformer, double circuit line, and finally the system is connected to the infinite bus. Okay. So we can actually draw the equivalent circuit of this system. How? Let's say this is our synchronous generator and the voltage is E dash, and the transient reactance of synchronous generator is XB dash. So we can represent it as JXB dash. Then we have also the transformer reactance JXT, right? And we have the double circuit line. So the both reactance values are X1, X1, JX1. And finally this is connected to the infinite bus, right? So this is the infinite bus voltage, and this should be connected here, and that should be connected to the ground. Okay. So this is the case. Equivalent circuit diagram. Now the system data is given. F is 60 Hz. H is the inertia constant, that is given as 9.94 megajoule per MVA. XT dash is 0.3 per unit. XT is 0.2 per unit. X12 is 0.3 per unit. V is the infinite bus voltage, that is 1 per unit. You can actually replace this V in terms of the complex form, right? The magnitude of V and the associated angle. And as we take this thing as reference, that's why this will be zeroing, right? And the magnitude is given as 1 per unit. And the P is the electric power delivered to the system, that is the P, that is 0.6 per unit, and PF, the power factor, is 0.8 and lagging. There is no damping in this system, so the P is 0 per unit. Okay. Then what is asked? Determine the maximum power input. Determine the maximum power input that can be applied without loss of synchronous. So what does it mean? The maximum power input that can be applied without loss of synchronous. Actually, this is same as the transient stability limit, right? Because the maximum input power that we can apply from PM0 to PM1 without loss of synchronous. That is actually the transient stability limit. Okay? That means here we have to calculate the PM1 minus PM0. This limit we have to calculate. Not that, first of all we have to solve the delta max, because whenever you will know the delta max, then you can know the value of PM. then you can take the difference of PM1 and PM2. That will be your transient distribution. And to find the delta max, you need to know the value of delta max, right? That isn't given here directly. So no delta naught term is given. So we have to calculate the delta naught as well. That's why we have to start like this. So first of all, we have to calculate the transfer reactance or the equivalent reactance between the two voltage sources. That is this source and this source. Okay? And what will be the equivalent reactance? These two are in parallel and both have the equal values. So simply it will be divided by 2. Then this result will be in series with this xt dash and xt. So it will be simply xt plus xt dash plus x1 to our 2, and you will get 0.6 by 1 unit. Okay. Then the next step is to calculate the apparent power S. So from the power triangle curve, you know that this is the theta, this is your real power, this is the apparent power, and this side actually gives you the information of reactive power, right? So you can apply the cos theta formula. That will be the base P over the hypotenuse S. So if you take the S in that side, you will get S is equal to P over cos theta. So look, P over cos theta is actually the power factor, right? P over power factor. Now obviously this S should be a complex quantity, right? That means it should have magnitude as well as the angle. So this will give you the magnitude. So what will be the angle? Angle will be this theta. This theta will be the angle of the complex part, right? That you can write like this. Angle cos inverse power factor. So if you calculate P is 0.6, power factor is 0.8, you will get 0.75. And from here you will get the 36.87 degree. This is the apparent power S. Then you have to calculate the I. Yes, you can write it like this. V I conjugate, right? So what will be the I? I conjugate will be first of all S over V. If you just remove this conjugate, then you take the conjugate to the right side. It will be simply I is equal to S conjugate over V conjugate, right? Like this. So what is the value of V? V is the infinite pulse voltage. You know that the magnitude is 1 by V, and there is no angle. Angle is magnitude. And what is S? S is this. So if you take the conjugate, so there will be minus sign here. So it will be simply 0.75 minus 36.87 degree. Then we can calculate the excitation voltage of the E prime. Okay, how can we write this formula? This reactances are represented by only a single reactance, that is X equivalent, right? And there is your infinite pulse voltage, and you have the E prime here. So you can apply the KVL, right? So it will be simply E prime will be equal to the voltage drop across this. That will be the, if the current is I, so it will be Jx cube I plus this voltage, right? That will give you the value of E prime. So E prime is V plus Jx cube I. If you calculate, you will get this. Now from here, this is the magnitude of E, right? And this is the angle. So what is this? So actually, one means actually here both the values are in actually complex form, right? Okay, so complex means both it will have the magnitude as well as the angle. Okay. So here this angle, what is this angle? Which parameter actually is represented by this angle? This is actually the delta, right? Because this E means the magnitude of E prime and the angle of delta, right? This is the angle delta. And as this is the calculation at the initial stage, that means this is actually the delta naught, right? This is your delta naught. So we have calculated the delta naught. Now we will solve delta max using the iterative solution technique. So For that, first of all, we have to take an initial guess for the delta max. Let's say that is 100 degree. Okay. And if you convert it into radian, it will be 1.7453 radian. Okay, you can do it easily. Because 180 degree is actually 3.1416 radian. So 180 will be 1.7453 radian, like this. Now you have to fill up this table. So the first column is for the iteration number k like this. Then the value of delta max at that iteration k, and this is your initial delta max that you have taken here 100 degree, that is corresponding to the 1.7453 radian. Okay, that is here. Then in the next column you have to calculate this. Why? Because this you have to calculate this thing, this delta max, that is equal to c minus f of delta max, that is equal to that k value, right? And in the denominator side it will be df over d delta max evaluated at delta max k, right? That's why this thing you have to calculate. Also you have to calculate this. This should be actually k, right? To calculate this value. That means you know this expression. This is actually this thing. So here you will just put the 1.7453 radian. That is the value for this delta max. And for what is this thing? This is actually the left side of this equation. This thing. So here, in the place of delta max, just place 1.7453 radian. Okay, then you will get this. What is the delta naught? Delta naught is actually 16.79 degree. You have to convert it into the radian because all the calculations are there in the radian, right? You can do it in the degree, no problem. But here all the calculations are given in radian. That's why here you have to convert this degree into radian as well. Okay. And what will be this c? C is actually cos delta naught, right? This is your c. This c is given here to find the value of delta max. So if you know the delta naught value, so you will find the c. Now with this information you can calculate the delta max at k, and what will be the updated value of delta max for the next iteration? The addition of this and this, right? You will get this. Then in the rightmost column you have to check the difference. So the previous value was this, and now this. Difference of this is this. Okay. Okay. Let's say you have the tolerance value as in the 10 to the power minus 6 times. Yeah, this will be given. Okay. And if it is like that, that means this difference should be below this one, and this is 1.18. That means we are still far away from the solution, right? So now proceed with the next iteration. So in the next iteration, this is our delta max at k, right? Then with this value again we calculate this thing. Then also we will calculate this. Then addition of these two will give you this, right? Now this minus this will give you this thing. So you are getting this delta. That is okay. Same thing because this minus this. So you can see that the difference is getting less, right? That means you are close to your final solution. So if you proceed like this, so maybe at iteration number 6, you will see that now the difference is 4.6 multiplied by 10 to the power minus 6. That means it is below this one, right? And now you can stop here and you can take the updated value. Delta max at iteration number 6 as your final delta max. So this is the delta max. Okay. Now if you know this value, you can calculate the delta 1 to pi minus delta max, right? This pi is 3.1416 minus 2.1963. It will give you the this one. Okay. Now what will be the PM1? PM1 will be P max sin delta 1, or you can write P max sin delta max. The same thing, right? What is P max? It is actually the magnitude of E prime, magnitude of V divided by x equivalent, the transfer factors. You know the magnitude of E prime, that is 1.35. You know the magnitude of V, that is the 1 per unit. And what is x equal to this, right? So if you put all these three values here, you will get the P max. Then you know the delta 1, so you will get the PM1 as this. So now what will be the transient stability limit? PM1 minus PE0. Why PE0? Because at the initial operating point, our PM0 and PE0 are actually same, right? So this PE0 is given. This is at the initial operating point. PE0, that is 0.6 per unit. So the PM0 is also 0.6 per unit. So the difference between these two will be the transient stability limit. Okay. Now, if you plot the power angle curve with these values, then you will get this thing. So this is your PM1, and this is your PM0 or PE0, right? And this point is point A, initial operating point. At that point, what was the delta naught? It was 16.78. No, 16.78. And what is the delta max? If you just again convert it into degree, this and this, then you will get the delta max is 125.83 degree. This delta 1 is the 54.16 degree. Okay, this is the case. And obviously, as this is at the limit, right? So this area and this area should be same, right? Because we initially we actually applied this equal area Platinum method, and then we actually got the expression of delta x, right? And as this is at the limit, so if you just cross this boundary for PM1, then the system will be in the unstable state.
Sir, for example, just make the PV line for the
Okay. Yes, you can do, but it's better if you just show at least one or two items. Okay. So he is asking that without doing any hand calculation in the string, can we just fill up the string, right? Like this. So you will just do the calculation using the calculator, and you will just put the calculator, right? That is your question. Okay. But you can just do at least one iteration using the screen. Okay. At that time, if you do any mistake here, you will get some mark for that calculation. If you just prepare this table and there are no calculations in the screen, then if there are some mistake here, I will not be able to give you any mark because there is no other calculations, and you have a mistake here. So how will I know that you have applied the wrong formula or it is just a calculation mistake? But if you apply the formula and if you do the calculation at least for one iteration, at that time I will be sure that okay, your formula is correct, but maybe while pressing the calculator you have done mistake, that's why you are getting the wrong result.
So if you do the hand calculation and don't make the table,
Okay, so if you do the hand calculation for all of the iteration 6, then no need to prepare this table because you have already done it. So that's not a big deal. The deal is to understand this problem, okay, precisely, because this is the most easiest problem of this chapter, and in the future slides we will see a bit difficult things, and the problems will be a bit complex in the coming lectures. Okay. So any other questions up to now? So we have solved example 11.4, and actually this assignment is given here. You can solve it through hand calculation. Okay. And all the steps and processes I have shown it in this class. So I think we can do it. Okay, now the next topic. This is the application of ESC, equal area criterion. So look how actually we are proceeding in this slide. In the first few slides, okay, we have just developed the idea of equal area criterion, right? Then look, we have understood the graphical representation of ESC. Then we started the application of ESC. What was the first application of ESC? The determination of transient stability limit, right? So using this technique, using this concept, we determine the transient stability limit. So this is, you can say that this is a useful tool, right? And now we will study another application of this ESC, and that is the three-phase fault at one end of the transmission line. Okay. So before that, what we have studied so far, we haven't included any fault in our system, right? What we did, we just increased the mechanical input power from this value to this value, and we observed the system response. We saw that how the system is responding. But now we will inject some fault intentionally to actually observe the system response due to that fault. Okay, that will be our topic of discussion from now. Okay. So now this is another application of ESC. That is the three-phase fault at one end of the transmission line. Okay. So and after that, so this is the fault at one end. One end means, so these two lines are actually the transmission lines. Okay. And this fault, F is represented here for the fault. Okay. So this is occurring at one end. Let's say this is the sending end, and this is the receiving end. Why this is sending end? Because this is the generation end, right? From the generation side, we send the power, and this is the receiving end. Means here we have the load or the customer are actually here. Okay, so this is actually the receiving end. So this fault, in this case, the fault is near at the sending end. Okay. Then in the next case, that will be discussed in the next class, we will see that the fault is away from the sending end. That means it is at the middle, the transmission line. Okay. So we will consider these two cases. This is the case 2. The fault is at the middle, but the fault actually away from the sending node. Here the fault is near at the sending node. Actually the fault is at one end of the transmission line. Okay. Okay, we will discuss this thing. Okay, we will discuss the type of fault that we are considering here in details. Okay. So now just read out this thing. Assume a generator is connected to an infinite bus through two parallel lines. Okay. These two are the parallel transmission lines. The input power PM is constant here. So in this case, we will assume that the PM is constant, and the machine is operating steadily with a power angle delta naught. That is the initial operating point. So at the initial operating point, the rotor angle was the delta naught. Okay, that is said here. Now, a temporary three-phase voltage fault occurs at the sending end. At the sending end of one of the line. There are two lines. So this fault is occurring at one of these two lines. Okay, and that is represented by this point F. Okay. What is this fault? Temporary three-phase voltage. So we will actually discuss these three terms in details. So what does it mean by temporary? Temporary means the fault will last for a few seconds, and in the next moment there will be no fault like this. Okay. So what can be the example of the temporary fault? So we can take the first example as the thunderstorm. Okay. We know that actually this thunderstorm vanishes within the blink of an eye, right? It comes and it vanishes quickly like this. So whenever the thunderstorm comes and if it touches this line somehow, then that line will be short circuited, right? There will be a short circuit path to the ground. So this is the ground. So there will be a short circuit path due to this. And after in the next moment there will be no thunderstorm. So the fault will now be clear. And at that time we will assume that again the lines are actually again healthy. So the lines will be intact like before. Okay. Then again if there are any thunderstorm, there will be short circuit path. Okay. And if it vanishes, then again the lines will be intact like this. So this can be one example. The second example can be, let's say a tree. Let's say a tree is here. near this transmission line. Okay. Let's say there is a heavy storm outside, so due to that the environment is experiencing heavy wind. Okay. And due to that heavy wind, let's say this tree is swinging right and left continuously. Okay. So whenever it is swinging in the right, it is getting touched with this point. Whenever it is getting touched, that means this tree is connected to the ground with its root, right? So whenever it is touching this point, that means there will be a short circuit path again to the ground, right? Whenever in the next moment, due to the wind, again the swing tree is going to the left, so there is no connection again. That means the fault is clear. At that time, we will assume that the system is again in the intact position, like before the fault, right? So again, in the next moment, the tree will touch this point. Again, it will disconnect. So this can be another example of the temporary fault, right? Have you understood this thing? Okay. Now, what does it mean by voltage fault? Okay. Voltage. Have you heard about this name? Voltage. Maybe you have heard. So voltage fault means there will be no fault impedance. That means, let's say this is the point where the fault is occurring, okay? And from this point to ground there is a short circuit path. So this is our path for the fault, right? In this path there is no impedance. If this is the case, that is called the voltage fault. Okay. What is the significance of this voltage fault? So in this case, the fault current will be maximum or minimum. This fault current will be maximum. That means with this zero fault impedance, we will get the maximum amount of fault current possible. Okay. So that is actually the maximum fault current we will experience in this case. If there is non-zero fault impedance, at that time the fault current will be a bit less. Okay. So why we are discussing about this voltage fault? Because we are considering the most severe type of fault, and we want to observe the system response at that severe type of fault. Okay. That's why we are considering about the voltage fault. So any question about temporary fault and the voltage fault? Right. So now, what is actually the three-phase fault? Okay. Now let's come to your question. So three-phase fault means, we know that three-phase means we have three-phase wires, right? So in this side we have the generation end, and this is the load side, right? So from the generation end, using these three-phase wires, we are supplying the power to the load, right? Now three-phase fault means all of these three phases will be short-circuited with the ground. Okay. So this is the three-phase fault. Now another type can be single line to ground fault or double line to ground. Okay. So let's think about the single line to ground fault. Okay. So this is the case for the single line to ground fault. Only one line is affected, but other two lines are heavy, right? So if this is the generation end, if this is the load end, so your job is to supply the power from generation end to the load end, right? Now, in this scenario, will there be any power flow from the generation end to load end? From generation end to load end, will there be any power flow? No. The power flow will be completely zero. In this case, will there be any power flow?
Yes.
Yeah, there will be power flow. There will be some amount of power flow across these two heavy lines, right? So we will see that here the power flow is not actually completely zero. Due to this one affected line, obviously there will be some hamper in the power flow, but it will not be completely zero. Okay. So which one is the most severe one? The three-phase fault is the most severe. Okay. That's why again the three-phase we are actually considering the most severe type of fault. We can take the single line to ground fault or double line to ground fault. That will be less severe. Okay. But considering considering this three-phase fault, we are actually dealing with the most severe type of fault. Okay. Now look at the combination of these three: temporary, three-phase, voltage. So this is the most severe type of fault. Okay. We can also increase the severity by this. Okay. Can anyone say what can be the most severe than this? Or is this the most severe? Can there be any severe fault than this combination? Yeah, exactly. This is temporary, right? So if we consider the permanent fault, that will be the most severe. Permanent three-phase voltage faults. That means our system will be completely ruined. There will be no power flow. The system will be completely damaged. Okay. So, but we are not considering that permanent fault. Why? Because we want to see the response of the system. That means whenever there is no fault, we will see the response of the system. Then during the fault, we will see the response. Then after the fault clears, we will see the response. So we want to see the response before fault, during fault, and after. That's why we are considering about the temporary fault. Okay.
So for this temporary fault, will the circuit breaker be?
Okay. So actually, the circuit breaker operation is a bit different. So the circuit breaker will treat. Okay. So there are different types of circuit breaker, right? You will see some relay that can operate in terms of time. It will see about how much time the fault is there. So if the fault clears before that time, so the circuit breaker will not operate. But if there is another circuit breaker, let's say that is only responsible due to the current flow, and if sees any current that is beyond that limit, so that circuit breaker can be tripped. Okay. So there are many type of circuit breakers in your system, right? In your practical system. Some actually senses the fault in terms of time or length, or some actually senses the fault in terms of voltage or current or speed, like this. Any other question? No, right? So now let's read out the 4 points that is given here. The first point is the power transmitted to the infinite bus is 0. Okay. Why 0? Because this is the three-phase fault, right? So all the lines are affected, so there will be no path to flow the power from generation into the infinite bus. And infinite bus means there we have the load. Okay. So the power transmitted to the infinite bus is completely 0. If this is true, then what will happen to the power angle curve? It will correspond to the horizontal axis. Why? Look at the power angle curve. This is the power angle curve. So this is the value of P, right? So the P is increasing with respect to the delta up to pi by 2. Then again it is decreasing. But due to the three-phase fault, we know that the P is completely 0, right? So how this figure will look like? It will be a horizontal one like this, right? So it will be like this. Okay. That is said here. Power angle curve corresponds to the horizontal axis. This is during the fault. Whenever there is fault, the power flow will be 0. So the power angle curve will correspond to the horizontal axis. Okay. We'll see all this thing in the power angle curve here. No problem. We'll see all these things here in this figure. Okay. Now, let's say our P is 0, right? But there is a non-zero value of Pm, right? That is constant here. We have assumed this value as constant, Pm is constant. Okay. So that means all the time the Pm is now higher than P, because P is now 0. If this is the case, the machine will accelerate. Why? We know this equation, swing equation, that will give us the information of the rotor acceleration. We have some constant parameter here, then Pm minus P, right? If Pm is higher than P, then the rotor actually accelerates. If P is higher, then rotor decelerates, right? In this case, the rotor will accelerate, means the rotor speed omega will be higher than the synchronous speed. If this is the case, the delta will also increase, right? Also, there will be some stored kinetic energy. So that's why the fourth point, the speed, the omega, the stored kinetic energy in the acceleration phase, the rotor angle delta, all three will increase, right? This omega will increase, stored kinetic energy will increase, and the rotor angle will also increase. Now, What is our assumption? When the fault is clear, so as this is a temporary fault, so at some moment this fault will be cleared out, right? So at that time we will assume that both lines to be intact. That is, both lines are assumed to be intact when the actually fault clears out. Okay, this is our assumption. Now, any question up to now? Now let's move forward. Okay, now we will actually consider three scenarios. One will be the network before fault, the network during fault, and the network after fault. Okay. So what is the network during fault? Before fault, it is same as before. So this is the figure of our single machine infinite bus system. From here we can draw the equivalent circuit. Actually, this is called the per phase equivalent circuit. Why per phase? Because if this is the three-phase system, so each line actually corresponds to three phase, right? But here we are drawing only the per phase equivalent circuit or one phase. The other two phase will be identical to this. Okay, so this is the per phase equivalent circuit. So look, we can easily draw it, and we can calculate the transfer reactance. It will be xd dash plus xt plus x12 divided by 2. So this is the synchronous generator. This is the infinite bus. So this is the load side. So what will be the power? P max. P max will be this, right? And this is P1 max is actually the power flow during before fault. Before fault. This is the before fault. So this value will be obviously non-zero. Then let's consider about the during fault case. So fault is occurring here. In the first case, we are considering that the fault is occurring at the sending end, near at the sending end, okay, of any of these two transmission lines, either here or here. So we are considering the fault is here. So now the fault is here means this line will be directly connected to the ground. So this is the ground, right? This is the ground. That means from this there will be a direct connection to the ground, right? And this line is intact. So there will be some reactance here. We are not bothering about this reactance. Why? Because let's say the current that is coming here in this node is I. Then there are two branches, right? I double dash, let's say the current across this will be I double dash and this is I single dash. So which one will be higher? I dash or I double dash? I dash will be higher. Actually the most accurate answer will be I double dash will be completely zero. And the I is equal to the I dash. That's why we are not bothering about this reactance, because there will be some non-zero reactance. Whatever the value, this current will be simply zero, and all the currents will follow across this one. Okay, that means the current or the power is again returning to the system, and the power is not delivered to the infinite bus of the load, right? That is the case. That's why in this case, the P2 max, the power flow to the infinite bus is 0. Okay. Now again, actually this is the per phase equivalent circuit. Okay. This is only for one phase, and the other two phase will be same. Why? Because we are considering about the three phase fault. Okay. So have you studied the balanced fault and unbalanced fault? Can you say this three phase fault is balanced fault or unbalanced fault? This is actually the balanced fault. Nice. For the balanced fault, we can analyze only the one phase. The two phase will be same. Can you recall actually maybe you have solved some problem for the balanced fault and unbalanced fault, right? So for the balanced fault, we can analyze only one phase. Okay. And for the unbalanced fault, we have to analyze all three phases, right? So as this is the balanced fault, that's why we are drawing only the single phase. Okay. And in this during fault case, the power flow will be completely zero. Then the network after fault. So the network after fault, we have some assumption. What is that? When the fault is clear, both lines are assumed to be intact. So it will be like before. Okay. So the network remains the same as before fault. So this is exactly same as before fault. So we will have some non-zero value of power flow. That is this. It is exactly same as the before fault. So any question for these three slides? So we have discussed discussed the three scenarios: the network before fault, network during fault, and the network after fault. Any question or any confusion?
Sir, so during the fault, will there be any power drop from 15 bus?
Yeah. Will there be
The
any?
second, will there be any power drop from 15 bus?
There will be no power flowing to the incoming bus because
From 3, the incoming bus act as a source on that bus.
okay. Actually, what is the concept of this infinite bus? Actually, we have discussed the single machine system, right? That's why we have kept the single machine. All other components, let's say all other sources, loads, and other things we have represented it by infinite bus, right? Okay. So if there are more generators, okay, they can act as source and they can meet the demand, okay, but that is not our target. We are focusing on in this single machine. Let's say we have the demand here 100 megawatt, and all this 100 megawatt is coming from this single machine. We are considering this case. Now if there is any fault, so there will be no power, so this generator will not be able to deliver any power, so it will actually deliver 0 megawatt. That is our task. But obviously, if there are more generators, they can participate to actually meet this 100 megawatt. That can be the case. Okay? But actually, we are not considering that case. We are considering that whether this single machine is able to deliver the power or not. And during the fault or whenever the fault occurs, what will be the response of this single machine? So, any other question? No, right? Now with this three scenario, we will now plot the power angle curve for this case, okay? And actually this thing we will discuss in the next class. And we can conclude to here, slide number 31. In the tomorrow's class, we will start from here. But you have to remember that we are actually discussing this case, right? The three-phase fault at one end of the transmission line. And we have three scenarios: the before fault,